All right, we did talk about the logistic growth model a little bit earlier in this chapter, but we're going to look at it a little bit more these last three. So if I were you, what I'd be writing down is the logistic growth model, and either of these equations are the same. I would probably just write this one, f of t equals c divided by 1 plus a times e to the negative t power. Right, look at my top left drawer. They have. So A, B, and C are going to be constants, so there will be numbers provided to you. C and B have to be greater than 0, and E is that button on our calculator. So what happens with this logistic growth model is that as you're starting to put really large numbers in for t up here, this denominator is going to get really close to 0, which means the entire fraction gets close to the c on the top. So what I would write if I were you, I'd write c equals the horizontal asymptote. So those graphs are going to kind of level out to the c value. And so the value of a can never exceed the c. And so c is what we call the limiting size, or the capacity. The model will never be greater than c, which is that numerator. All right, so an example. This is the model of the spread of the flu in a particular town. So if I were going to write this equation down, f of t equals 30,000 divided by 1 plus 20 e to the negative 1.5 times t power. And it says that f of t describes the number of people. So this is the number of people. And t is the number of weeks. So it says part A says how many people became ill with the flu when the epidemic began. So when it began, what time value would that be? 0. So all you're doing for letter A is putting t equal to 0, which would be f of 0, which is 30,000, divided by 1 plus 20, e to the negative 1.5 times 0. And then you're going to get your calculator out and start typing this in. And I think it's always easier if you can use that fraction button on your calculator. So alpha y equals and then number 1. And we would do 30,000 on the top. And then 1 plus 20. And the exponent, or we need the e next. And then second ln gives us the e. And then negative 1.5 times 0. And we would talk about people, so we would just follow the normal rules around it. You can't have 0.57 of a person. So we'd round that up to 5 or above, give it a show, 1429. Now again, one of the things that we're going to really stress this last week is if we have a word problem, again, according to Harrisburg's rubric, we have to make sure we're kind of making a summary statement at the end. So we have to make a little statement that says, we can say 1,429 people were ill when the epidemic began. Okay, again, that statement, closing statement is super important. All right, part B says how many people were ill by the end of the 4th week. Again, T is in weeks, so it's as simple as just doing F of 4. So we would do 30,000, 1 plus 20, e to the negative 1.5 times 4. And then again, we would type that into our calculator. So it is as simple as, if you remember, if you press second enter, it pulls up the last thing you typed in. So you could type second enter in, pull that up, and then scroll over and change the 0 to 4. So we have 28,583 people after the 4th week. And again, make that closing statement. You can say 2,000, about 28,583 people were ill by the end of the 4th week. And then part C, the last thing it says, what is the limiting size? So that capacity. Again, where do we find that capacity or that limiting size? What part of our fraction? The C, which is up here, right? So 30,000. And they told us here 30,000 is the amount of people in the city. Okay? They're not always going to do that, but in this case, the town had 30,000 people, so the town only has 30,000 people. We can't have more than 30,000 people get the illness or the flu. Okay? So, part C, we can say 30,000. Yeah.
Is that always going to be the number?
The numerator is always the capacity, the highest it can be. All right. One more example, and you'll have to work. All right. So in a learning theory project, psychologists discovered that the equation f of t equals 0.8 divided by 1 plus e to the negative 0.2 t. So we're going to write this equation down. So it's the model for describing the proportion of correct responses, f of t, So this is correct responses. After T learning trials. So T is the number of trials. All right, letter A says find the proportion of correct responses prior to learning trials taking place. So if you're saying before any learning trials taking place, that would be 0 learning trials taking place, so we're finding f of 0. It would be 0.8 divided by 1 plus e to the negative 0.2 times 0. And we can type that in our calculator. Alpha y equals, get that fraction bar. And we have 0.8 on top. On the bottom, 1 plus e, the negative 0.2 times 0. We get 0.4. So again, we make that summary statement, so we can say prior to learning, there was 0.4 correct responses. So chances are this would be like an average, okay? There would probably be multiple people doing this experiment, and that would be the average if you average it all up. Part B says find the proportion of correct responses after 10 learning trials. So again, that means we're just going to put 10 in for the T. And then pushing that second enter repeats everything we just used, and we can just scroll over, change the 0 to a 10. So we have 0.7 as our correct responses. So after 10 learning trials, there was 0.7 correct responses. And then part C again says what's the limiting size, the proportion of correct responses as continued learning trials take place. So again, we find that what part of our fraction? C, which is at the top, so 0.8 would be our correct responses. Okay, so the first thing I want you to work on is page 531, numbers 38 to 46.